So for ChIP-seq, you typically use Bowtie because it's much faster than BWA. For variant analysis, you're typically going to use BWA MEM because it's considered a bit more accurate than Bowtie. Most people use BWA MEM. It works with long reads, and that's also typically what you have when you want to do variant analysis. And it can work with the alternate haplotypes in case you are working with human data. So what about the BWA MEM parameters in Galaxy? Let's take a look. So here in the tools section, you just type BWA MEM. Here we are, map with BWA MEM. So the reads have to be at least 100 base pairs to use this algorithm. So what are the different parameters here? Well, the first thing that he needs to know, of course, is an index, so the genome that you want to map to. So you either select a built-in genome, and as you can see, there's a lot built in here, again, a lot of plants. But also human and also mouse, if you take a look. So you either choose here a built-in reference genome, or you can also, if it's not supported, you can also upload your own FASTA file. And then you use this one. Prerequisite here is that the FASTA file is in the history in Galaxy. When it's in the history, he will recognize it and he will suggest it here. You have to tell him whether you have single-end or paired-end data because the mapping is quite different depending on what you have. So we have single-end data here, in this example. And then you have to give him the FASTQ files, so the input files, the files that you want to map. So in our case, we have multiple FASTQ files here. So we are processing the chip and the control sample in batch because we uploaded them to Galaxy as a collection. I can here, by clicking this button, ask him to search for a collection. Which FASTQ files are we going to use here as input? Well, the clean FASTQ files. So after running Tremomatic on them. If you do have paired end data, and I'm going to go back here. There will be a number of extra parameters that you have to set. So for one, he will expect 2 FASTQ files as an input. You have to give him the data in pairs because he is going to use both files of a pair for the mapping. Why? Well, because he can then use the benefits of doing paired end mapping, the extra information that you have when you have done paired end sequencing. So what is the extra information here? You know that the 2 reads that form a pair have to map on opposite strands and they have to map in each other's proximity. Now, what does proximity mean? You also have to explain what you mean by this. And this is what you do here. So you have to give him the distribution of the fragment lengths in your library. Because what is the distance that you expect between 2 reads that form a pair? Well, the length of the fragment that they come from. And then we have these parameters. So here you can tell him what kind of data it is. So we are focusing in this course on Illumina data. So we would go here for simple Illumina mode. What is this read group information? What does this mean? What is a read group? A read group is a collection, a set of reads from one sample that was sequenced on one lane in the flow cell. That's one read group. So if your sample was split over multiple lanes, over 2 lanes, for instance, then you will have 2 read groups for that sample. So BWA MEM is one of the few mappers that can handle this easily when you have multiple FASTQ files per sample because of using multiple lanes on the flow cell for the sequencing. Other mappers, like for instance STAR, cannot handle this. So, but BWA MEM can do this, and it can itself concatenate the FASTQ files that come from one sample into one single FASTQ file. So when you have this kind of data, you don't have to use the concatenate dataset tool in Galaxy. You can immediately go for BWA MEM, and BWA MEM will be able to handle your multiple FASTQ files per sample. And for variant analysis, most of the downstream tools will also be able to handle these read groups. So for variant analysis, if you have multiple FASTQ files per sample, this is not such a big issue. But for RNA-seq analysis, your mappers will freak out on that. So for RNA-seq analysis, you have to concatenate them before you do the mapping. I'm going to ask him here for the full list of options just to show them to you. So these are all the options that are related to the mapping itself. So BWA MEM automatically chooses between V mode and end mode depending on your data. So you don't have to tell him, he will decide himself. The parameters that you see here, all the different parameters, they are very similar to the typical parameters that you also have when you do a BLAST. Because BLAST alignment and the alignment that Bowtie and BWA do is very similar. So for instance, when I here expand the scoring options, you will see a lot of penalties for gaps, for initiating gaps, for ending gaps, and parameters for mismatches in the alignment. So the same parameters that you would also see when you look at the BLAST parameter form. Now, to be honest, I never changed these default settings because the default settings were chosen in such a way that they are ideal for mapping high eukaryotes data. And when you do variant analysis, in most cases, you will work with human or with mouse, but it will be higher eukaryotes. So default settings are perfect here. You don't have to change them.